Hello, and thank you for joining me. My name is Gadi Singer, and I lead cognitive computing research at Intel Labs. And today we're going to talk about the next generation of machine intelligence. And for that, we're going to take a little trip in time from the last decade into the coming decade, and in space. We're going to start from the abstract concepts, but very fundamental, of understanding, intelligence, knowledge, and cognition, and go all the way to what are the architectures that are required in order to support it effectively. There's little doubt that this last decade has been the decade of the deep learning. With the algorithmic changes, with the convolutional neural network and LSTM, and of course transformers coming, it drove a complete change in the landscape. It also created a lot of innovation in frameworks like TensorFlow and PyTorch and Paddle and others. And it even drove new hardware, whether it's GPUs or CPU with special units or neural network processing units. And it has applicability everywhere in all segments, in transportation, in financial services, in infrastructure, in all aspects for the coming years. However, despite all the great achievements and the great potential for impact going forward, there are some fundamental limitations, and I'll just mention 4 of them. One is scale. The compute required for the largest model, the model size, are growing about 10x every year. That is not sustainable. Moving from 100 million to 300 million parameters in BERT, a year later to 10 times that, a year later in GPT-3 to 175 billion, a year later to 1.6, 1.75 trillion parameters is not sustainable as a trend. Another aspect is robustness and trustworthiness. Because there's such a dependency on the distribution during inference to be matching what was seen during training, there are many limitations for out of distribution, for domain transfer. There's brittleness in the model that is not acceptable in many applications, and this needs to be addressed. A third aspect is human-machine interaction, the ability to operate together as AI is coming closer into the workplace, into home, into cars, the ability to explain itself. And finally, higher cognition. Deep learning systems of today do not have the capabilities of reasoning and higher cognition that are required for many tasks. And for that, we need to see how we're moving forward. You're still not sure that there is a new era coming? Let's just take 2 sources to support that. The first is Yoshua Bengio from his NeurIPS 2019 keynote. He talked about System 1 type of capabilities. And in System 1 capabilities, those are habitual, those are instinctive, those are unconscious and fast. You know what to do, the system knows what to do, it does that. But this is current DL. Where we are moving to is System 2. Those are the type of capabilities that require more reasoning, more planning, more thinking. They are slower and logical. They require more conscious attention. This is the future of AI. Another source is DARPA. DARPA has been talking for the last few years about the move from a second wave, which is what we know today, which is statistical, to the third wave. And the third wave is cognitive, is adaptive, is contextual. So this next wave is going to be those type of System 2, more cognitive systems. As AI gains understanding, it becomes more human-like. So let's call this next level cognitive AI. And imagine what those AI systems would be able to do beyond the statistical correlation of today. They will be able to understand language with its meaning, not just predict the next word and the next phrase. They will be inherently multi-source, gaining and consolidating source of information, and multimodal, images, natural language, and other sources of information. They will be able to integrate common sense and have reasoning done on the common sense knowledge. They will be able to adapt to new circumstances and tasks through better generalization. And they will be able to explain themselves as they generate new outcome. They are also expected to be more robust and more customizable due to the use of symbolic entities and abstracted concepts. All those capabilities of anthropocentric cognitive AI systems can be achieved by the use of knowledge that is structured, explicit, and intelligible. Since we're talking about knowledge, let's just go back for a minute and talk about how is knowledge different from information and data. Data are just the basic bits that are received or out there. For example, you look ahead and you see gray and green and yellow bits. Information is when all the data is structured. So when you look ahead, you see a dashboard of a car. And through the front window, you see that there's a traffic light, and the traffic light just changed from green to yellow. Knowledge is organized information in a way that allows you to be productive, to take action based on experience, to generalize it, learn new actions. So in this case, what do? Do you push on the accelerator or do you stop? That's part of the knowledge. And specifically, we'll talk about deep knowledge, which are knowledge constructs that allow an AI to continuously acquire new information, organize its view of the world, comprehend meaning, and reason on this knowledge. And to understand the importance of this, let's distinguish between recognition and higher cognition. Recognition has a lot of shallow data. In the example that I gave, all those bits are shallow. They just have their color and their location in a 2 or 3-dimensional, and you get all this in. But you need very deep compute in order to extract features and to have this put into things that will create those structures of a traffic light and a dashboard and so on. Cognition, in order to make decisions, to understand, requires deep knowledge. And the reasoning is based on this knowledge. To discuss more about knowledge and how it's structured and how it creates this intelligence, let's do it with an example in mind. And we'll take it from healthcare, from bacteria and bacterial infection in the lungs. And even today, deep learning capabilities are doing a great job in just identifying aspects of images, be it X-rays or CT scan. But we want to take it much further. We want to have cognitive AI that use knowledge for continuous learning, for observation, for interaction with people, and for the diagnosis. To better understand how knowledge can support higher intelligence, let's look at a model of the knowledge. And we'll talk about 6 dimensions of knowledge that are all required in order to create this support. If you start from the bottom left, there's the descriptive knowledge, which is the static view of what's in the world. And then there are models of the world, which is the more dynamic view, how things are changing. There are the stories, which are the longer narratives about the world. And then the meta-knowledge, or knowledge about knowledge. You've got context and values and priorities, which we'll discuss. And finally, the concept references that tie all the other 5 dimensions together. Let's start with the descriptive dimension. Descriptive knowledge is about what is out there in the world. It could be facts, all types of facts, but also entities that are abstraction of those. And it is including in taxonomies. So you have taxonomies of the plant world, and then particular plant family, and then particular plants within it. And that gives you so much power and ability to go, when you find a new plant, to know many things just by understanding this world of knowledge and the taxonomy and the relations. It also is supporting ontologies. When you have entities, what are the relationship between those entities? And specifically on bacteria, what are the types of bacteria? What are the characteristics? How do they look like in terms of images? How do they interact with others? Or if we take a higher concept of bacterial infection, how is this informed by what we know about bacteria? And what type of impact does it have on the lung, on the health? All that information is part of the descriptive knowledge. The third dimension is about stories and scripts. And those are longer narratives, and they can have some twists and turns, but they are guiding our life. As a matter of fact, there's a view that people learn best through stories. And stories could be some epic stories about religion, the first people who created something, like found the bacteria. Or there could be mundane scripts. What happens when somebody comes to a CT scan? What do they need to do? What do they do later? What happens in one case? So those longer narratives are very important for us to be able to understand a situation in the moment, as well as for the AI to be able to predict what is likely to happen next. Stories represent shared experience and inform people's values and their actions, and they are required for the AI system to be able to do the same. We talked about 3 types of knowledge. Now let's talk about meta-knowledge, or knowledge about knowledge. And the first of those is context as well as source attribution. Context is a frame around events or other types of knowledge that facilitate their interpretation. 3 masked men go into a bank branch. Is there trouble ahead? Well, it depends. If it's pandemic, you have that context, then no, they're just following the guidance of what's required. If it's not during a pandemic, it's a different story. So context give you that environment to interpret events. And there could be global context, and that is pretty static. For example, can you turn on a red light, have a right turn? Well, it depends. If you're in California or some other states, if you stop at a red light, like a stop sign, you can turn after you've stopped and watched. If you're in several countries in Europe, you're in big trouble if you do it. So the geographical context, and there are other types in a medical environment. There are guidance from the country, and there are guidance that are local. And then there's the local context, the transient. And that is what is relevant and important for the task at hand. For example, if you're looking at a medical repository or information, you have a particular question to ask. That is the context of your current search. If you're looking at a video, you can ask what is happening in the video. But if it's a video of what's happening in the store, you can ask, when did we last see that woman with a purse? Because she lost her purse, and I want to ask that particular question. So that gives you a local context. The combination of the global context and local context give a lot of the support for the intelligent response. Also, we need to take care of data provenance and the source attribution. Sometimes if you look at a left-leaning news outlet and a right-leaning news outlet, reporting on the same event, you would think they were in different places, because the sources of information matter to interpreting the information. And when you talk about medical environment, there's some advice that comes out of popular magazines, but there's also advice that comes from the reputable, well-sorted, well-vetted articles that are much more reliable. There's some naive assumption of systems today that information is information. So if GPT-3 is reading 45 terabytes of information, it's all information. But we know that for an intelligent interpretation of the world, that is not sufficient. The second meta-knowledge is about values and priorities. Each of those concepts, items in the knowledge that we talked about so far can have a value and can have a priority. And that informs our decisions when we need to make choices, when the AI system needs to make choices. And when you have a value system, it could be good to bad. It could be opportunity to threat. It could be some ethical scale or consideration. But it's important to have the ability to assign those weights or those values to various items. For example, in the healthcare situation, patient's life, patient's discomfort, dignity, privacy, the financial impact. All of those are ingredients that might have some global value, like life is higher value, higher importance than discomfort, but could have some local value itself. So for example, financial impact. It could be that Jeff Bezos might have a different priority to financial impact than somebody else. And this really allows us to create a value system for the AI. We talked about 3 dimensions of knowledge, 2 overlays or meta-knowledge, and how is it all tied together? Through the concept reference. This is the one place where everything related to the same concept ties together. So if we take example bacteria as a concept, everything around the knowledge database that has to do with bacteria, what it is, how it operates, what are the stories about it, and all of that, all of it ties into a single reference so that you can get from any information on bacteria to another piece of information on bacteria. And of course, those concepts are tied in an ontology. So bacteria, as a concept reference, is tied to concepts such as bacterial infections that are built on top of it. So this is really the structure that ties the whole dimension together. We cover knowledge. Now let's go to understanding. What is understanding? Understanding is about the ability to create a worldview expressed with rich knowledge representation. In a way, be able to model inside the machine, inside the person, the complex world that is outside. The other capability of understanding is to acquire and interpret new information and to enhance and continuously update this worldview, because the world around us is very dynamic, the interests are growing, so part of understanding is the ability to continuously update this internal view inside the machine or on us of what's happening outside. And the third is the ability to effectively reason, make decisions, and explain both our existing knowledge as well as in real time new information coming from the outside. So far we talked about knowledge and understanding as if people and machines can have the same type of capabilities, but how do we really approach it with AI systems? What type of architecture will support it? And to have a better understanding of that, let's look at the classes of AI architectures. And let's start with class 1, which is the most prevalent one, of fully encapsulated information. This is your neural network, which has pre-training and fine-tuning, and all the information is gathered in and sitting in the parametric memory of the neural network. For example, a language model that can identify, can translate, can generate, and everything is self-contained within the neural network. While this is great, it can do so many things around differentiable information, about continuous spaces. It has some limitations when it comes to volume, as we saw with the growth of the model. And this is where class 2 comes into play. Class 2 are AI systems with semi-structured adjacent information. For example, Wikipedia as an information repository. In those systems, rather than try to ingest and bring everything, all the data, all the semantic information into the neural network, there's a recognition that information that is hardly ever used can stay out there, and through links, through a retrieval mechanism, you can bring it when you need it. There are many systems today that are built that way. There are actually some benchmarks like Efficient QA, where all the winning solutions were retrieval-based. But still, this does not solve some of the challenges of cognition, of having complex models and relationships and taxonomies. And for that, you need class 3. Class 3 are AI systems with deeply structured knowledge. This is where you have a neurosymbolic systems with a neural network and with a deep knowledge base. And the deep knowledge base is populated from external sources. It could be that it's an existing database such as Wikidata or DBpedia, or it's something that you're constructing. But once you have all those relationships, all those entities, all those dimensions built in, you can have this system perform all the required tasks. So, does it have to be one of those three? Let's step back and look at what are the levels of knowledge that we need to include in a system. I believe we can partition knowledge, all knowledge, to 3 levels. The first, most immediate, is this knowledge that is used for instantaneous response, for intuitive, habitual response. This is what Benjo called System 1 after Kahneman. An example from the medical field, a doctor is asked, can we give this medication with this fever reduction medication? He answers immediately, yes, you can. He's done it multiple times. He knows, doesn't have to think about it. Similarly, this is the knowledge that sits in the neural network. Within the neural network, it's ready to use. Within the inference, it already gives the answer. The second level of knowledge is the knowledge that requires some consideration, some thinking, some reasoning. This is the system 2. Doctor, can we give this medication with this medication? Let me think about it. Yes, I know the mechanisms of interaction. Yes, after thinking about it for a little bit, I can tell you you can give those 2 medications to the patients. Similarly, for the AI system, this is the ability of a neural network to operate very closely with the knowledge base and together to create those reasoned responses. The third level is when you need access to outside the system or outside the person. Doctor, can we give the patient this medication with this new medication that was approved last month? Let me get back to you. I need to go check online or in the book, and then coming back and saying, yes, I've checked the external sources. This is the next action. Similarly, for AI system, there's the need to go outside to all those broad resources out there and be able to extract as needed new information in order to provide the reasoning. This 3-level knowledge, or you can call it the thrill K, is the key to build cognitive AI systems that provide all those functions. Guided by those 3 levels of knowledge, we can envision the architecture of the future. And this architecture of the future, we can call it the thrill K architecture, will of course include a neural network, will have a deep knowledge base that provide all those dimensions of knowledge and interacting with the neural network, and it will have to have access to the external world, to the Wikipedia and YouTube and the sources of medical data and all others, because the world keeps changing around it. And with this architecture in place, we will be able to establish the capabilities required for cognitive AI. So bring it all together, a new set of cognitive AI competencies will emerge in the coming 5 years, unlocking systems that are more explainable, that are able to apply a higher level of autonomous reasoning closer to what humans have in particular areas. This is not AGI, it's not conscious machines, but much more capable cognitive machines that are able to do reasoning over deep knowledge structures, including facts and declarative knowledge and causal knowledge and conditional and contextual knowledge and relational knowledge and all other aspects that we talked about. And by applying the 3-level knowledge hierarchy, the thrill K hierarchy, we can build systems that will look at the continuum of knowledge and reasoning to achieve cognitive AI. Recall what cognitive AI will provide us beyond statistical correlation, understanding of language with its meaning, being able to integrate multiple sources and multimodality, integrating common sense knowledge and reasoning, adapt to new circumstances, new tasks, being able to generalize, explain itself, be more robust and more customizable. So with that vision in this direction, AI technologists should look at the capabilities required over those architectures to elevate AI to higher cognition and to cognitive AI. And everyone, just imagine what you will be able to do with cognitive AI at hand. We would love to continue this dialogue. And there's so much more to be understood and progress on that. And you can reach us on the Intel Labs site or the LinkedIn account for Intel Labs or my personal LinkedIn account and on Medium and towards data science. And together, let's push the state of the art into more capable, accountable AI systems for all. Thank you.